Okay, so semi not knowing where we stopped, except for Kimchi said I wrote this last line here in black. I'm going to sort of go back real quick because I know that you guys will have to watch this in 2 installments. We started out with this equation here, some ethylene getting together with some oxygen, burning just like a torch, making carbon dioxide and water. And when we did this, we found out that the heat for that entire reaction was negative 414 kilojoules per mole. Exothermic wants to go, gives us a bunch of energy as it does that. Now, the question was, is there a way to actually figure out how much energy is just in the C2H4? How much energy would be in forming that from its elements? And I said, all we need to do is get a system of equations, and those systems must take into account that the parts would sum to the whole. And so I said, let's presume we can get ethylene from carbon and hydrogen, carbon dioxide from carbon and oxygen, and water from hydrogen and oxygen. And we wrote down those equations, and we said, look, there's no way of dealing with oxygen because how do you form an element from itself? It makes no sense. So there really isn't an equation there. It just is. Now, if we wanted that delta H naught formation, we just have to arrange these guys right here, these three, plus the original, such that we can isolate the one we want, which is this guy. So we set out, first of all, by taking our original equation, which had the C2H4 on the left, and flipping it around so that it shows us making it instead of consuming it. And that's this equation right here. And then as Ben pointed out with the intuition is, hey, look, if we're flipping around the reaction, if it were exothermic one way, then it would have to be endothermic the other. So just switching the sign. This is where I said, keep track of the signs, pluses and minuses, that'll be important. The other two reactions, the carbon dioxide and the water, we could use them in their form straight away, meaning element plus element makes compound, because what we're actually ending up or trying to do here is to cancel things on the left and right. But as noted in our reaction, we're making 2 carbon dioxides. Therefore, when we're trying to make the sum of the parts equaling the whole, we were going to have to multiply that by 2 as well. Now, all that means is in a normal situation where the delta H naught of formation is negative 393.5 kilojoules per every 1 mole, because we have 2 of them, we'll just multiply the whole thing by 2. Twice as much stuff, you get twice as much energy. And the same thing with the water. We wanted the 2 waters here to cancel the 2 waters there. So we're just going to multiply its heat of formation by 2 as well. By summing all 3 of these equations, we end up actually with that 4th equation that we wanted. That one right up here, we're like, hey, if we could just get this guy from the elements. And it turns out taking the reaction and subtracting out the parts, we'll get to that last part. So essentially, if you guys remember the whole idea of partial pressures, the summation of all of those equaling the whole, you could solve for any piece as long as you knew what the atmospheric pressure was. We're just doing the same sort of thing here. So if at the end of the day, the summation of these 3 reactions as written end up with the one we want, we will just take, if these 3 add up to the one we want, we'll just take all of their H's and add them up. And if we do that, we find out that the delta H naught of formation for this piece is negative 856.6 kilojoules per mole. Which means that if you got the carbons and hydrogens and ended up making ethylene, this again would be exothermic. So what we've done here is taking the parts and the wholes to either solve for the whole thing or solve for a piece of the missing puzzle. And this is exactly how they do a lot of these heats of formations is it's really not, it's kind of like unreasonable to think that you could throw some carbon and hydrogen into a room, do something and say, why don't you make some ethylene gas? Those elements would go like, no. But what you can do is you can say, hey, ethylene that I already know exists, why don't I burn you in the presence of oxygen, make carbon dioxide and water, use the energies that I know that these guys make to back out what you would have been. Does that make sense? Chef, just say yes. Oh, Chef isn't here. Kimchi, say yes.
Yes.
Thank you. Okay. So now that I've done that, now that I have used an overall reaction to determine a piece of a reaction, what I want to do now is figure out what a reaction would be from any given pieces. So now that I've done that, how about predicting a reaction from its parts? Okay, and this I'm actually going to do with one thing that is pretty well studied, and then discuss why we would do something like this in just a moment. So let's take, let me get into purple. Let's take C2H5OH, good old alcohol, plus oxygen. We're going to go ahead and burn that. You'll notice, by the way, a lot of these involve burning, and we'll show you why in a second. H2O and CO2. I want to know, what is the delta H of this reaction? What should I expect for this? And of course, just to remind ourselves, we'll have 3, 2, and 3 for the balanced equation. Now, what we're going to do is we can look up the following. These are in books, so these values are easily found. I want to look up the delta H naught of formation of C2H5OH. And that is going to be negative 277.7 kilojoules per mole. I'm going to look up the delta H naught of formation of CO2, and that is negative 393.5 kilojoules per mole. I'll look up the delta H naught of formation of water, and that's negative 241.8 kilojoules per mole. And I will just remind ourselves that the delta H naught of formation of oxygen is nothing, right? You can't form an element from an element. It just doesn't make sense. Okay, so just like we did before, I want to take each of these reactions right here, these guys right here, and I want to write them in terms of being formed from their elements so that I can use their delta H's. But now what I wanted to do is I wanted to match the overall equation up top. So use the delta H naught of formation equations for these three to end up with our initial reaction and get its delta H of reaction. Now again, it's not a delta H, not a formation. It is a delta H, but we can actually put a knot. And the reason we can put a knot is because this guy right here is a 1 mole. So we can define it based upon the alcohol being the 1 mole. Okay. So what I'm going to do is I'm going to write C2H5OH goes to make 2 carbons, half of an oxygen, and 3 hydrogens. Now, again, all these delta H knots of formation are to form that substance. We are not forming it, we're actually going quite the opposite. So its delta H that we looked up as negative 277 now becomes positive 277 because we switched it. So that delta H naught is now positive 277.7 kilojoules per mole. Right, because we flipped it. And the reason we flipped it, just to remind us, it was on the left-hand side of the equation. Now, the other two, the CO2 and water, we're going to be able to write them as we should from the elements to make the compound. The only difference here now is we got to worry about the coefficients. Okay, we're going to worry about those, but we know how to tackle that. So we're going to write that 2 carbons or plus 2 oxygen go to make 2 CO2s. Well, I guess actually let me write it like this. Let me just write the C carbons plus the hydrogens make the CO2. And let me go ahead and put its delta H naught of formation, which can stay how it is negative 393.5. And then note that because we have 2 carbons and we need those to cancel out so we don't have anything bad going on there, that we should multiply this whole thing by 2. Which means if we do it to one, we have to do it to the other. So again, trying to get those carbons, the 2 carbons there, to cancel out the 2 carbons there. I'll do the same thing with the hydrogens plus half of the oxygens. We'll go to make an H2O. Keeping that delta H naught of formation as it is, negative 241.8 kilojoules per mole. And hopefully you'll see that in order for these hydrogens here to cancel out, I would need to multiply this times 3. So this one here gets multiplied by 3. Now, as we look at that, we have almost everything here. Take a look at the oxygens though. Hopefully you guys can see that 3 times a half, right? 3 times the 1/2 makes 3 halves. This right here makes now, what is that? 4 halves. And 4 plus 3 is 7 halves of oxygens. But I have one of them gone there. So 7 halves minus 1/2 is 6 halves, which is 3 oxygens at the end of the day. If you didn't see that, hang out after and I'll show you the math on that. But at the end of the day, this does give us the C2H5OH plus 3 oxygens goes to make 2 carbon dioxides and 3 waters. At this point, we're going to add, you'll notice though that it's not going to be quite as much energy as we'd hoped. While every piece was exothermic if you were making it from the elements, one of them we had to flip around. And so it's going to sort of essentially take away from the overall reaction of that rate of the system. And at the end of the day, this delta H naught of the reaction is equal to negative 1234.7 kilojoules per mole. And as we all know, if you light alcohol on fire, it is going to give us energy out. Which means it's exothermic and wants to occur, wants to go. All right, so before I make you guys really mad, do we have questions about the what that we are doing? Is everyone okay with me switching around equations and multiplying them and flipping signs? Anybody uncomfortable with that? Now, what about the why? Is anybody a little cautious on the why we're doing it? Are we still here? Kimchi, say yes.
Yes.
Sure. Because for all I know, I was talking to the ether again with my internet down and waiting for it to dump me out. Okay, so since you guys want to ask that question of the why, I just want to point out that oftentimes people will try to figure out, hey, if I do X, Y, or Z for this reaction, enthalpically, as far as the bonds are concerned, from the before and after standpoint, as far as they're concerned, do they want to occur or not? Does it want to go? And enthalpically speaking, you want that to be negative, to be exothermic, to release the energy, because Mother Nature is lazy, wants to go to the lowest energy state that it can. In this case, without doing anything, if you went to the books and you actually looked up the standard heats of formation, the enthalpies of formation for various different compounds, you could technically have an idea of whether it wants to occur as you are trying to make it go. And so you can already start the game off by knowing if you have a chance of this reaction working in the first place. We'll talk about the other part a little bit later where entropy may or may not help us out. But just enthalpically, just talking about the energy of the bonds, we can go and we can look up all sorts of little pieces here to a puzzle to make an overall equation to ask ourselves, does it enthalpically, does it want to do what I'm asking it to do? And this is actually something people do a lot of, where they go and they say, hey, I wonder how much energy I could get out if I burned this or if I did that to it. They'll go and they'll find all the pieces. They'll build their equation, multiplying by 2's and 3's if they have to figure out, look, if I'm going to make this reaction go, what can I expect? Now, I know that took us, with our neat little break and everything, like a gazillion amounts of time to do. So you want me to make you mad? Check it out. I'll make you mad and then you'll be happy. Trust me. There has to be an easier, faster way. You guys think there's an easier, faster way?
Yes.
Thank you, Kimchi. Now, do you actually know where I'm going with this, Kimchi?
I think so. Is it with the products and reactants and like the moles?
Absolutely. So that is really good insight. The easier, faster way is, look, any of the delta H naughts of the reactions is equal to the delta H naught of all the products minus the delta H naught of any of the reactants, which is exactly what we just did. If you look at it, what did we do? We took the products, the negative, oh, let me get my thing. The negative numbers here. We took all those products and we minused the negative number, minused the reactants. It's glorious. So what did that look like? So from above, we had the C2H5OH plus 3 oxygens. It goes to make 2 CO2s and 3 H2Os. Okay. If we said that the delta H naught of the reaction is equal to the delta H naught of the products minus the delta H naught of the reactants, products, well, let's just be very, very plain. That's 2 carbon dioxides and 3 waters minus the C2H5OH and the 3 oxygens. Right, there's the products and there's the reactants. So all I have to do now is plug in the numbers. So I have 2 times negative 393.5 plus 3 times negative 241.8. I'm now going to subtract out the reactants, which is a negative 277.7. And just for kicks, I'll write 3 times 0. That's for the oxygen. And in the end, you end up with the negative 1234.7 kilojoules per mole as the delta H naught of the reaction.
Why? Why did you make us do all of this?
Oh, Isa, I love it when somebody's like, oh, you're such a jerk. We spent an hour doing something. Okay, so the reason why I made you do this is you have to understand the reasoning behind any, quote, shortcut there is out there. Have you taken calculus yet?
No, I failed it in high school.
Oh, no, okay. But if your teacher were worth their salt at all, they started building up calculus by, if you remember those Riemann sums before we got up to the integrals, you had to understand that by summing the parts on infinitely smaller levels led to the integral. Without that, then you would just do something without the understanding. And so what I'm trying to do here is to show you the underlying principle as to why, when I have an equation up here that's a methanol plus 3 oxygens gives me these 2 carbon dioxides and 3 waters, why is it that I am allowed to, at the end of the day, just say, oh, products minus reactants? Now, keep in mind, that's the same thing I've told you from the beginning. is when you're looking at the difference in the enthalpy, the delta H, that's the difference in the energy of the bonds before and after the reaction. And so if the energy after the reaction is lower than it was before, it wants to occur. But what I've been able to do, hopefully here, even though it was painful, what I've hopefully been able to do is to show you that I'm taking the final resting place minus the initial starting place and ask myself, did I give off the energy I need to be thermodynamically, enthalpically favorable to occur? And I mean, really, this is going all the way back to proving that thing we did before. Remember this, where we said, hey, products and reactants, we have the activation energy, right? And we said there was an energy change here. That might as well just be a delta H. So what I started out with as a conceptual idea with you guys, without sort of mathematically proving it, what I intended to do with this, and what I hope you can appreciate, even if it was painful, kind of like the cigar box experiment, is that while yes, there is a simple formula, you must understand at least where it comes from. Otherwise, the knowledge you get out of just using the formula is useless. Isa, remember when you were learning to balance something like Al with a 3+ and oxygen with a 2-, and you were doing this in high school?
Yeah.
What did your teacher tell you to do? How did you balance it? Isa? Isa? Oh, she went silent on me. She's like, I'm not answering that. All right, I'll answer for her. Usually, your little high school teacher said, oh, you just swap them and you drop them, and it just becomes Al2O3 because you do the swap and drop. Well, that was the shortcut. Now, if you've been with me since Chem 110, you notice that I never, ever say that. What I say instead is, what is the least common multiple of 2 and 3? Because if all you ever do is swap and drop, then if I gave you something like lead with a 4+ and oxygen with a 2-, and you just did the cutesy little swap and drop, you'd end up with Pb2O4, which is not the case. So I like showing you guys the reasonings behind what will end up being this guy right here. We love this guy. We're going to be using that a lot. And of course, you are going to remember that you have to use your stoichiometry. Did Issa just like leave the building or what? Oh no, she's down there. Okay. So this is the reason why, Issa, that I go through sometimes the very painful things, because oftentimes if you learn the shortcut or just the end result and you don't know why it's happening, it's sort of a hiccup and a misstep in your education. So I'm trying to make sure we have the good foundation for when we go forward. I know it was a long-winded explanation, but did that sort of answer why I did all this painful, Isa?
Yeah.
Okay. Are you still mad at me?
No.
Okay. It would have been okay if you said yes. All right. So now here is where I want to get to this, just because it's going to be useful for the lab. I'm double checking with Josh before we make this lab live for you guys. And this is the enthalpy of reaction for magnesium reacting with hydrochloric acid. This is the basics of what we're going to talk about right now, which essentially is bomb calorimetry. And this was for Dallas, who's not here. Let's talk about bomb calorimetry. Okay. So bomb calorimetry, calories, right? We want to know the energy inside of a thing. So you want to know how many calories are in a Big Mac. Now, nutritionists will tell you to just burn it. Which is one of the ways they do this. So what do we mean by just burn it? And I'm telling you, you will just burn it. But why would a nutritionist tell you to burn your Big Mac? Does anybody here work out? Tristan?
Yes.
Yes. When you work out, there are other synonyms for working out. Can you think of any synonym that starts with burning?
Burning calories.
That's right, burning calories. So we talk about burning calories because we eat food. We eat food, right? We burn it in our body. We burn it in our body and we respirate. Oh, anybody here take bio? What do we respirate out? That's right. Carbon dioxide and water. We breathe in oxygen and we take that oxygen, we combine it and we exhale out carbon dioxide and water. You guys see the patterns here? Do you guys see what's going on? I got a CO2 and water over here that I'm going to make. And oh, what have we been working with? Oh, CO2s and H2Os. Most of the things that we want to figure out how much energy they are typically are combustion reactions. Now, there are others, but most of the things we care about are combustion. So what this really is this is some sort of CXHYOZ compound, our good old hydrocarbon, plus oxygen goes to make good old-fashioned CO2 and water. So this is your Big Mac. This is your air, and this is your breath. I guess breath is without an E, right? There we go. Okay, so why is it called a bomb calorimeter? Check it out. I'm going to make a nice little drawing here. Ooh. So I'm going to make myself, actually, I'm going to freehand it. All right. Let's see. I'm going to come here. And then I'm going to make a guy here. So what I'm doing is I'm drawing a very simple bomb calorimeter. Here we have, of course, good old-fashioned water. I'm going to put a thermometer in here. And I'm going to get myself an electrical wire. This electrical wire is going to come in. And inside of here, I'm going to have 1,000 PSI of oxygen. And I'm going to put my requisite Big Mac. Oops, there's no K on there. All right, and this here is an electrical wire. Okay. So what happens with this bomb calorimeter? Okay. Put your sample on the wire. You zap it hard enough to let it react with the oxygen. Heat is released. Actually, I'm going to do this. Heat is released. Water absorbs it. Temp goes up. Which means that the delta H of this reaction, the amount of energy it is giving off, is going to have to go somewhere, and it is going to the mCp delta T of the water. So what do? You take a look at this. You get yourself a container. You fill it up with 1,000 psi of oxygen. You stick your, well, I should say you stick your sample on it first. Fill it up with 1,000 psi of oxygen. Stick it inside of a water bath. Note how big the water bath is. Zap it. Let the thing burn. Watch it heat up the water. Figure out the temperature difference of the water. If you know how much water was there, you know its heat capacity, you know how much it changed in its temperature, you then know how much that reaction was giving off. Okay, if we know how much the reaction is giving off, here's the reaction, right? We already know these numbers right here, which means if we know the reaction, then we know our Big Mac. We're watching water heat up to tell us how much that reaction gave off. To back out from the heats of formation of carbon dioxide and water, what those pieces of your organic material were actually comprised of energetically, and that's how they know how many calories are in a Big Mac. I think that's pretty cool. If you don't have an imagination. Now, for Dallas, who is probably sitting over there going, duh, or asking my questions, yes, what happens here, Dallas, is, first of all, you probably insulate the top of your container. Not only that, you would actually perform this experiment in such a way as to figure out how much energy this container here would absorb before it gave it to the water. You would also figure out how much the container of water loses to the atmosphere to account for all of that. You would also account for exactly how much energy you put in with your electrical wire so that you could get rid of and account for all of the things that are not your Big Mac, so you can just focus on the Big Mac. So you can do all of that. And when you get to an analytical chem course, you will absolutely do something like that. I've seen it in lower level courses when professors are being actually extra nice to you. But let's talk about the other two things of this. Why is it called a bomb calorimeter, Dallas? Look at that PSI, 1,000 PSI. Well, there's 14.7 PSI per atmosphere. So if I take 1,000 divided by 14.7, that's about 68 atmospheres worth of pressure. If something goes wrong, that blows up. Hence, bomb calorimeter. Now, why make it so high? Oh, Harvey, why would they make that so high, do you think? Rio. All right, Kimchi,
Yeah.
why would they make the pressure so high?
So that it'll happen faster. I don't know.
Well, yeah, no, not about the fastness, but there's a couple things we want to avoid. First of all, we want to make sure that you have so much oxygen there, that's not even close to the limiting reactant in this system.
Right.
Okay, so we're flooding it with a whole bunch of oxygen just to make sure. I mean, that's a lot of oxygen in there. And also, remember that as we look up here at this equation, we will be consuming some of this oxygen, okay, in order to make this. But we don't want a drastic enough change that we can see it. How much do you really think of this 1,000 PSI you're going to consume in a tiny little reaction? Remember, we're not actually putting a big piece of Big Mac. We're putting proportional pieces on there. You're not going to deplete any of the oxygen there. You might go from 1,000 to 999.8. Okay, nothing. Now, why 1,000? Because we said this heat capacity was at constant pressure. And this is how they get a constant pressure heat capacity for the water is they are doing this in such a way that the pressure of your system won't change. And your overall system remains basically static, and you can just focus on the stuff. Okay. I know this is a weird day, so I'm just going to go to the example here that I have. And let's see how a bomb calorimeter might work. Okay. A 10-gram sample of dimethyl ether is placed in a bomb calorimeter and ignited. It looks like C2, H6O, plus 3 oxygens, goes to make 2 carbon dioxides and 3 waters. The heat released changed the temperature of 250 mils of water by 8.6 Celsius. What's the heat of formation of dimethyl ether? The heat released changed the temperature of 250 mils of water by 8.6 degrees Celsius. What is the delta H naught of formation of dimethyl ether? Okay. So, things we know. Means we looked them up. the delta H naught of formation of CO2 is equal to negative 393.5 kilojoules per mole. The delta H naught of formation of H2O is negative 241.8 kilojoules per mole. And finally, the heat capacity of water is equal to 4.186 joules per gram degree Celsius. Okay. Now, we have that the delta H of the reaction is equal to the MCP delta T of the water. Or another way of thinking of it is that the
Can you go back up?
yeah.
That's good. Thank you.
Okay. Is that the heat of the C2H6O is equal to the positive heat of the water, right? The water is going to gain and the other is going to lose. That's another way of thinking of this. So what I want to do is calculate how much energy that water happened to have. So if we look at the MCP delta T, hopefully you guys realize that the 250 mils is 250 grams of water, 4.186 joules per gram degrees Celsius, and we had 8.6 degrees Celsius. And I'm going to have to calculate that. 250 times 4.186 times 8.6 is equal to, I basically have 9,000. 9,000 joules, because our Celsius cancel and our grams cancel. That's how much energy was there. Which means if that's the case, then the delta H of the reaction is negative 9,000 joules. Okay? But we wanted delta H naught. We want to know how much that is. So this means we need to scale it to 1 mole. Because these are all written in kilojoules per mole. So 10 grams of C2H6O is 46.08 grams. And that's 0.217 moles. So again, when you're doing these calorimetry experiments, you're not always going to be working with the exact amount that you want, specifically the 1 mole's worth. What you do instead is you use a portion of it. Well, everything will scale accordingly as long as you remember to go back to that per mole basis. So just as you would not put an entire Big Mac in that bomb calorimeter, you would take the proportionate amount of bread and meat and lettuce, special sauce, pickles, onions on a sesame seed bun. You would get all the pieces of those. They'll obviously be smaller than what a Big Mac is. You'll burn them, you'll get the energies, but then you will scale it back up to as if you had that 1 mole's worth of material. And that's what we're doing here. So now we take, where'd my glasses go? I don't even know. So now we take this 9 kilojoules, we divide it by the 0.217 moles, and this gives us 41.47 kilojoules per mole. And of course, that was actually negative. And so now we have the reaction overall. Let's get that C2H6O. So now that we have the delta H naught of the reaction, let's get delta H naught of formation of the C2H6O. Okay, so just to remind ourselves, C2H6O plus the 3 oxygens goes to make 2 carbon dioxides and 3 waters. Oops. We're looking for this delta H naught of formation. We know that this one is 0. We know that the carbon dioxide is negative 393.5 kilojoules per mole, and the water is negative 241.8 kilojoules per mole. We know that delta H naught of the reaction is equal to delta H naught of the products minus the delta H naught of the reactants. This is just math now, we're just solving. So the products, we have 2 times the negative 393.5 plus 3 times the negative 241.8 minus the reactants. Well, that's the delta H naught of formation of C2H6O plus 3 times 0 for the oxygen, right? There's the oxygen. Eventually, you guys can leave out the elements if that's what you want. That's totally fine. I like to put it in just for kicks. But we know that this equals negative 41.47 kilojoules per mole. So at the end of the day, the delta H naught of formation of C2H6O is equal to see if I did that right. I get negative 1554. Do I have confirmation? Oops, no, I have to do that. Hold on. No, sorry, negative 1471.
Yeah.
So what's really nice about what we've been able to do with this is we're now starting to piece together 2 or 3 concepts so that we can go many different ways. First, we look at the transference of heat just between a couple of things. Delta H's equals delta H's, or MC delta T's equal other MC delta T's. Today, we looked at how you can take the difference in energy of the enthalpic bonds between products and reactants and get an overall energy for a reaction. We also took an overall reaction and actually determined one of the parts of that reaction. And then we combined it together with what we learned before of the MC delta T's, meaning we can take this guy right here, a reaction giving off its heat to a watery system, watching that watery system, and by doing so, determine what happened to the reaction. And from the reaction, understanding the last piece of the reaction, which is the thing you actually care about. That's your Big Mac, or in this case, the dimethyl ether. So that's kind of cool. At least I think it is. Hey, that's all I have for today. You guys cool?
Yeah.
Yeah, brain full. Don't like this afternoon lecture. You like the morning lectures where you're all awake and everything's happy?
Yeah.
Sorry,
Morning
guys.
lecture's nice because it gives you actual motivation to get out of bed before noon.
Wait, so I'm like a personal coach here. I'm getting you out of bed. Yay, go team. All right. I highly doubt there's any questions about this because it's either like, yeah, I don't get it, I'll read it, or yeah, it's just math.
I kind of have a question.
Well, then kind of give it to me.
So the bomb calorimeter thing, when I was learning about that before, we learned like that, and we also learned about coffee cup calorimeters.
Coffee cup calorimeters, yep.
But I remember like just never understanding how that worked at all.
So the coffee cup or the bomb?
The coffee cup one.
So the coffee cup one is kind of interesting because, and in fact, when you, not this next lab, but the one after it, we'll do a heats of reaction where you can actually see that using 3 different reactions, you can prove that no matter how you add them together, they should all come together at the end. Basically, A plus B makes C type of a situation. And we do essentially have a coffee cup calorimeter. And that is, it's a styrofoam cup. It's open to the air. You're mixing a couple of reactants and watching their temperature change. The coffee cup is when you're not trying to ignite something, but rather when you are just trying to mix a couple of things and see the energy given off as those liquid reactants do their thing.
Yeah.
Because coffee cups don't have lids. So you're not trying to combust things there. What you're doing at that point is just trying to compare the energy in one system to the energy in another as the reaction takes place by monitoring the temperature change. And I think that might make more sense when we do the Hess's law experiment. I think that's 10 or 11. And I'll be releasing those out pretty soon. I don't know if that answered your question, Kimchi, but if not, we can hang out afterward and I can try again.
Okay, it's okay. It's not that important.
Your education is the most important, Kimchi. Well, I mean, you as in the class, not that Kimchi's, super special. I mean, you are special. I mean, oh, God.
Okay.
All right. Any other burning questions? Gherkin, are you all right?
Yeah, I'm all good.
All right, cool. Patrick? Yeah. All right. Well, then what I'm going to do is I'm going to
Wait.
get it. Oh, wait, someone's in a chat. What are they saying? Oh, afternoon lectures. No, I'm not doing afternoon lectures. I need to get going. All right, I'm going to stop the recording.
Do you actually have a bomb calorimeter